taking the conservation law, I took a domain, and then I was
Yeah, I think the conservation of energy would like kind of trace the path towards the conservation law. If you have energy conservation, you have mass conservation, you have momentum conservation,
yeah,
you
that's fine.
have
That's fine.
angular momentum.
Yeah, I'm talking in general, like how I was taking u any variable which is varying in this domain, then del u
Oh
in this.
yeah, you take like the derivative or something like that, and
Yeah.
you
So,
uh yes.
yeah, let me ask you one question. If u is any quantity that is changing in this domain, if u is any quantity that is changing in this domain, so suppose u is, this is delta v, small volume. So to write all the quantity in this domain, what we need to do, we will take the integration over this delta v, is not it?
Yeah.
And then the rate of change of this quantity defined in this domain was proportional to the flux function. So flux function was that the amount which is the volume of the variable u which is coming inside or going outside, outside from the boundary. So that was the flux function, and the second quantity was the source or sink. So the same way we are going to write the derivation of the heat equation. That's why this I explained in very detail. I don't know how, if you remember or not, but this thing I did in very detail, and you guys are saying that it is very clear to you. So each section is somehow related to each other, and I would like to ask you, please read unit first and two thoroughly, and always keep it in your mind, because unit 2, that was the conservation law, that is the base of the PDE which we use in the real life application. Like every model which is formed by a PDE, whether it is a Schrodinger equation, whether it is a reaction diffusion equation, whether it is a Berger equation, every model is formed by the conservation law. So I would request you to read the unit 3 thoroughly, please. Sorry. And again, I would say the same thing. If you feel difficulty that some topics are not clear to you, then please do ask to me, or you can send me an email that we need a revision of this topic. I will revise it again and again, don't worry about that. So ut minus Laplacian of u equals to 0. This is known as your homogeneous heat equation. And the second, ut minus Laplacian of u is equals to f. This is known as non-homogeneous heat equation. Here t is greater than 0 and the space variable x. So this is Laplacian, and what is how the Laplacian is defined as? It is defined as summation of del 2 over del x I square, where x equals to x1 dot 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 xn. So this I is varying from 1 to dot 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 n, and x is belonging to u, that is subset of Rn, is this u is open set. So basically we take the space variable belonging to the open set, because when we define the Laplacian of any function, we say that this is defined in open set, domain omega, which is open and connected, and also u is continuous on the boundary of this domain. U is defined in this domain omega, which is open and connected, and u is continuous on the boundary of the domain omega. So we cannot talk about the differentiability of this function u on the boundary. That's why every time we define the Laplacian, then we say that the domain is open. Okay.
Yeah.
And x is a space variable such that it is n dimension. This is u belonging to u. The unknown is, oops, just wait, x is belonging to u such that u is function of x comma t. So u is defined from u, and since t is also variable, so you need to take closed 0 open infinity to r. So this operator u is unknown function, and the Laplacian. Every time we define the Laplacian with respect to the spatial variable, so and the Laplacian of u, that is nebula u, is taken with respect to the space variable, with respect to the space variable x, that is Laplacian of u is equals to summation I varying from 1 to n del 2 u, del 2 u over del x I square. In equation, in the notes I have written it like this: summation I varying from 1 to n u x I x y. So this is written in the subscript form. Whether you write like this or you write like this, both are equivalent. So in equation second, the function f, that is mapping from u cross 0 comma infinity to r, will be known to us, because every time when we are formulating the system, the source or sink is known to us, will be known to us. So the one most important thing is that any assertions you have proved about the Laplacian, any property or lemma or theorem, so these three together known as assertion, that is proved for the Laplace harmonic function. You have any assertions about the harmonic function, is an analogous, but for sure it will be more complicated. Why the complication will be coming? Because of the first order time derivative of u. Because of the first order time derivative of u, it will be analogous to the Laplacian equation. It will be analogous to the Laplacian equation. Only the one difficulty will be, right, because here the solution is not going to be the harmonic function. The solution is not going to be a harmonic function. So everything will be similar, but there will be one more difficulty. And if you guys remember about that, we were defining the Poisson kernel. we were defining the poison kernel. Here we will define the kernel, but that kernel will be known as the heat kernel. So we are going to see a lot of terms that we have already done in the previous classes. So this is going to be the easiest topic, I think, for all of you. So it's an analogous statement about solutions of the heat equation. So let's talk about the physical interpretation of this heat equation. So the heat equation, this is also known as the diffusion equation. This is also known as the diffusion equation. Can anyone explain me what is the meaning of diffusion? What do you understand?
Something is the system is losing something.
Heat equation. It sorry.
Like the something is, well, not losing but moving, right? It's like
Moving, yeah,
something.
exactly, yeah, you're right. So what was happening here? What was happening, like here, firstly heat transferred in one cross section and then it is spread to the second cross section and then it is spread to the next. In the same way, suppose you take the color pollutant, and this is the river, and you take the color pollutant and you drop on the surface of the river. So what will happen? This color pollutant will transfer here and then it will transfer to the next portion, then again it will transfer to the next portion. So it will start to move from one place to another place, and at the same time this is either going to, like, the color pollutant, if the river is not moving with a constant velocity, even if it is moving with a constant velocity, for sure the color pollutant is going to reduce with the time, because some of the color pollutant will will move away from the boundary. So like you are taking the color pollutant, but at this point the same amount might not be present, the same amount might not be present because we know that the river is not going to be a uniform surface. The river is not going to be a uniform surface. In the same way, if you talk about the heat flow in this rod, in the same way, if you talk about the heat flow in the same rod, in this rod, so what will happen? It will move from this point to this point. Now the heat of this cross section, when when this process starts, so the heat of this cross section is going to be less than the heat of this cross section. It will achieve its saturation heat. It will achieve its saturation heat after a very long time, so such a saturation time is going to be a very long time. After that, the heat of this rod is going to be uniform, but that saturation time ts is going to achieve after a very long time, because if we are taking a very big and thick rod, then for sure the heat is not going to be just in 1 minute it is going from here to here. No, if it is a very big and thick rod, so it will start to transfer the heat very slowly, and in this moment when it is transferring heat from one cross section to another cross section, the heat at the next cross section is going to be less than the heat at the previous cross section. Is this physical phenomena is clear or not? Physically you can visualize this thing or not? I would like to ask. Are you guys able to
Yes.
hear? Okay. If anyone feel difficulty that this thing is not clear what I am explaining physically, then please do ask, because if I am writing something and doing mathematical calculation, then that is not a very important thing. You can do it easily at your place. So heat equation is also known as the diffusion equation, because in this we can see that some physical property, either it is the heat of a temperature, either it is the temperature of a rod, or it is a concentration of the color pollutant which we have dropped on the surface of the river, it is going to move from one point to another point, and or in another way you can say that it is going to spread in the domain, it is going to spread in the domain. So because of the movement or spreading of the physical property, that is heat or concentration of the particle, we call it a diffusion equation. Describes in typical applications the evolution in time of the density U of some quantity such as heat, chemical concentration, etc. If this U was subset of Rn, if we take another subset of this U, if V that is contained in U is any smooth subregion, the rate of change of total quantity within V equals the negative of the net flux through del V. Just focus on the last four lines. If V contained in U is any smooth subregion, then the rate of change of the total quantity within U, the rate of change of the total quantity, the rate of change of total quantity within U equals the negative of the net flux through the boundary. So what is the total quantity in the region V for any physical density V U? What will be the total quantity in the region V?
The flux multiplied by the total area.
Yeah, so the total quantity is going to be the area of, like, the integration of U, integration of U in the region V, isn't it?
Yes.
And the total rate of change will be d over dt of this quantity. Okay, so it means the statement is clear, because the statement should be very clear to all of you. So the total rate of of the quantity change of the total quantity within V, since this x is space coordinate and we are in n dimensional, so dx is basically dx1 dx2 dot 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 dx, and don't get confused with it. Okay, this is equals to the negative of the net flux through the boundary. Net flux through the boundary, because we take unit normal this unit normal. Just let me draw the figure and then it will be more clear to you. Suppose this is u and this is v. V is a smooth subregion of u, so v is a connected subset of u, and also v is taken to be open. Now if u, suppose u is density in this region v at any point p, so the total quantity, the total density in this region V is defined as integration of u v dx1 dx2 dot 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 dx, and because we are in n dimensional and the flux, so some volume of this quantity u is either going outside of the boundary, either will be going outside from this boundary, or it will be coming from the boundary. Now what we take, we every time take the unit normal, inward unit normal. So this is the unit normal, the direction is towards the surface. In that case, if it is an inward unit normal, so because of that this negative sign appear. This we take for the sake of convenience, and it depends on the flux function. According to this inward unit normal, we change our flux function. So that is just for the sake of convenience, so that when we transfer the equation on the left hand side, we can write it like ut plus divergence of f. So what is the divergence theorem? Can anyone tell me what is the divergence theorem?
The integral of the divergence, well, nabla dot the field integrated over the volume is equal to the integral of the boundary of a volume that's a surface. That's a closed surface integral of the field f, I don't know, f dot the differential area vector.
ds you can say, because if we are one-dimensional, then it is. So using this divergence theorem, it is basically we are taking the closed surface. So whether you write this like this or not, it doesn't matter, because in the very first statement I said that V is a connected set. If V is a connected set, so that gives us this property. V is connected and open set. So that's why I did not write. If we don't have idea whether it is a connected and open set or not, then we need to put this symbol. If you put it, then it is not going to create any confusion, but if you don't put it for the connected open set, still it will be true. So using the divergence theorem, this quantity can be written as minus of integration over v divergence of f d of x. Basically d of v is dx1 dx2 dot 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 dxn. So whether we write d of v or we write simply d of x, both are same. Now this is true for all the smooth region v. This is true for all the smooth region v. So simply we can write, and if we use the fundamental theorem of calculus, then what will be the derivative of this integral? Can anyone tell me? If now you guys need to know what is the fundamental theorem. This is very basic thing. If we use the fundamental theorem of calculus on this term, then what it will give?
The function itself.
No, how you write the fundamental theorem? This derivative will
The
pass.
integral from a to x of a function.
Mm-hmm.
That's
The value of u at the uh, upper limit.
extrema.
Yeah,
Yeah.
yeah, at the value of u at the upper limit. But since this boundary is a constant, so the derivative of the upper limit is going to be 0. In the same way, minus u, the value at the lower limit, and the lower limit is constant because we have a fixed boundary. So the derivative of the lower limit is going to be 0. So this will simply reduce to this form. This will simply reduce to this form, isn't it? These are very minor things, but this play a very vital role in your derivation, because even sometimes I can make a mistake, I can forget about the things. So that's why every time these are the very like basic line of the derivation, but this is very important. Just bring it out in the one side. Now this is the volume of any smooth region. This is true for any smooth region V. So we can simply write, if it is equals to 0, then ut plus divergence of f is going to be 0, as V is arbitrary smooth region, isn't it? Or you can write ut is equals to minus divergence of f. So I haven't written anything new. This is basically the thing which we derived in the conservation law. Now in many situations, like when we actually form a physical phenomena, in many situations this flux is proportional to the gradient of u. In many situations, this f is proportional to the gradient of u, but points in the opposite direction. Can it okay do you know the physical meaning of the gradient of any function?
Gives the direction
Mm-hmm.
of the
No,
maximum.
don't relate it to the divergence. I am just talking about what do you understand with the gradient.
That's the vector that it's pointing to the maximum amount of change.
Sorry.
That's a vector that's
Mm-hmm.
pointing to the
Mm-hmm.
maximum amount of change, rate of change.
You are saying the correct thing, but the only thing you are putting it maximum. So just this definition is very clear to you. I don't need to tell you extra things. So just try to understand. We define the gradient of a scalar function, isn't it? gradient is always defined on a scalar function, isn't it?
Yeah.
So when we define the gradient, suppose we are in n dimensional, so how we write it? Del u over del x1, del u over del x2, comma dot 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 del u over del xn. Now, what is the meaning of gradient? What does it represent? It represents the change of the quantity u in x1 direction, in x2 direction, in xn direction. We don't know whether it will be the maximum change or minimum change, because you don't know in x1 direction that this u is increasing or decreasing, isn't it? Suppose you are taking a rod in one dimensional, and then you say that the temperature of the rod at this point is less than the temperature of the rod at this point. So what is happening? The temperature of the rod is changing from this point to sorry, in this case the temperature is increasing. Suppose the temperature is decreasing, like you are talking about the cooling function. You reduce this heat, now it will start to cool down. So in that case the temperature of this rod is going to decrease in each direction, isn't it? So we can't say that it is going to be a maximum change, like it is going to increase or decrease. We just say that it represents the change in x1 direction, in x2 direction, in xn direction. If u is a scalar, if u is a scalar, so f is also going to be scalar if we are not talking about a system, isn't it? uh, I would like to say one more thing here. I took u is coming from u cross 0 to infinity, so I need to write del u1 over del x1, del u1 over del x2, del u1 over del xn. So gradient of u1. In the same way you will define gradient of u2, because gradient is always applied on a scalar function. So if gradient is applying on a vector function, it means this operator is applying on each element, on each element. So in the same way, if this is so f that will also be n function, and each are scalar, so the gradient will apply on f1, the gradient will apply on f2, and so on, it will apply on fn. So this is gradient of u in n dimension is going to be a n cross n matrix basically. So gradient of any function represents change in x direction. Now what I was saying that the flux function f is going to be is going to show the changes in the quantity u across the boundary. It is going to the flux function f shows the change in the quantity u across the boundary, so shows the change in the volume of the quantity u across the boundary. So now if we are in n dimensional, so it is going to show changes in all the n dimensional, isn't it? So that's why this f is proportional to the gradient of u. Is it clear, or shall I explain it again? Is this point clear how I am writing this? The gradient of f is proportional to the gradient of u. Okay. So in many situations f is proportional to the gradient of u, but point in the opposite direction. Again we are taking it in opposite direction. Just at this case we are assuming that the flow is from the region of higher to the lower concentration. Like here the temperature was high here, and then it was flowing towards the temperature because the temperature was low here, and then it was trying to bring a saturation state. In the same way, if you were taking a river and you drop a color pollutant here, then what will happen? This color, where this point where the concentration is high, it will start to move from this to this point. It will start to move from one point to another point, that is from the region where the concentration is high, like flow is from the regions of higher concentration to the lower concentration, higher concentration to the lower concentration. So because of that, when we write that gradient of u, f is proportional to the gradient of u but point in the opposite direction. So the opposite direction is coming from here, because it is our assumption. If you are saying that no, we are cooling this rod, in that case the temperature is decreasing, so in that case you will not take it in the opposite direction, like you are not going to take the negative sign, you will take the positive sign, because in that case the temperature is flowing from the region of the lower concentration to the higher concentration, because you are cooling this rod. So f is proportional to the gradient of u, the gradient of u. So this is a way, gradient of u. And since we are saying that it is moving in the opposite direction, so when you will remove this proportionality constant, you will say opposite direction minus will be coming, and when you will remove this proportionality constant, some constant a will be coming, and for the sake of convenience we are taking, without loss of generality, you can take a is greater than 0. Now if you substitute the value of this flux function in equation number 3, now substituting into 3.
When you make an argument with without loss of generality, the things
Yeah, so
uh,
uh,
that's always like a question that pops out of my mind.
okay,
Like,
yeah, I got it. I need to explain it. Don't worry. I need to explain it. This point
I
is,
have an idea, but
yeah, this point is clear.
oh yes,
Okay.
but the argument, like in general, when someone says like without loss of generality, I
Yes.
think like, oh yeah, if you need like in the logic steps you make, if
Mm-hmm.
you need in those steps to change
Mm-hmm.
that that I don't know, that part that you said that was like without loss of generality,
Mm-hmm.
then the logic steps hold.
Yeah, because just let me explain. So this statement is coming after taking this opposite direction. So without loss of generality, I'm saying a is greater than 0, because if you are saying that at some point a is less than 0, then it is going to violate this condition, opposite direction. So that's why, since it is very obvious from the line that u, f is proportional to the gradient of u but point in the opposite direction, this is a very obvious statement that f you simply can write it like minus del gradient of u. But since I said that it is proportional, so you need to introduce a proportionality constant, and I am saying that without loss of generality I am taking this proportionality constant a positive proportionality constant, because if at some point it becomes negative, then it will violate the condition that it is moving in the opposite direction. At that moment it will start to move in the like it will start to move in the same direction. So because,
Okay.
yeah, because of that I mentioned here without loss of generality. Like if you focus on the population problem, so you say that p is the population at any time t, then the rate of change of the population is proportional to the population itself, isn't it? Now when this is the population model, you remember?
Yeah.
So here when I remove the proportionality constant, I put a general constant k, and now I don't say that k is a positive or k is negative, because population can increase or population can decrease. So according to the increasing or decreasing of the population, this k will change its role. But here we are fixed that it is pointing in the opposite direction, so we have to have the negative sign. So because of that, here we are taking a is greater than 0. But here, since we don't know, because in the corona the population of a lot of country decreases, so this k is going to be negative. But another k, population of almost all the country increases, so k is greater than 0. So here we don't put any restriction on this constant, but here we are very sure that f is proportional to the negative of the gradient of u. So if at some point this constant is going to be negative, then you will say that f is proportional to the positive of the gradient of u. So that will violate your statement. So because of that, I am saying that without loss of generality, it have to have this. I don't know whether I was able to clear your doubt or not.
Yes,
So
thank you.
substituting this f into equation number third, I will obtain u of t is equals to minus divergence of minus a gradient of u. Now a is a constant, so with it will come outside with the minus sign. I will left with divergence of gradient of u. So gradient of u is a vector quantity, because divergence always apply on a vector quantity. So the divergence of gradient of u is, what will be the divergence of gradient?
Laplacian.
Laplacian. So this is your heat equation. Most of the time we take like, just for the sake of convenience, we take for a equals to u, it is the heat equation. But you can take a simply. Now again, just open your assignment 8. So you can see that there I am writing the heat equation in the second question, but I am writing like this. So it is obvious that this is a and that is positive, because it is the square of some real number. It is square of some real number. So that is automatically positive. So in Brownian motion, the heat equation appears. So basically, um, in Brownian motion, again, I am going to explain you the Brownian motion. In Brownian motion, the heat equation appears. Do you guys have idea about the Brownian motion? Anyone? Have you heard about the sentence Brownian
Yes,
motion?
of course.
Hmm?
Einstein studied that.
So
Yeah,
what?
yeah.
Yeah. So what happens in the Brownian motion? Would you please explain so that everyone will get?
Um, it's the random movement of particles of pollen from
Yeah. Yeah.
from flowers
Mhm.
suspended in a fluid.
Yeah. So when the like, suppose what happens in the Brownian motion, it is the random movement of the particle. So suppose you have particle in any medium, like whether you are talking about the particle which are transferring the heat in a rod, either you are talking about the particle about those color pollutants which you drop on the surface of a river. So what it does, suppose it is the particle that is that is starts to move and go here and transfer it heats to this particle. This particle goes and transfer this heat to this particle. This particle goes and transfer the heat to this particle. Suppose that this particle goes and transfer the heat to this particle. So basically what it is happening in the Brownian motion, it is a random movement of the particles and how they behave. The one particle collides with the other particle and it transfer its energy to the other particle. So that's what was happening in the that's what was happening in the heat equation in a rod, temperature distribution in a rod. In the same way, there are a number of Brownian motion like stochastic process where the heat equation arrives. So that's why finding out the solution of the heat equation is really a very important thing in the physical phenomena. Next, we are going to write the fundamental solution of the heat equation. If you guys have any doubt till this point, like any physical interpretation or mathematical interpretation, you may ask to me. And if it is clear, then I am more than happy.
But the Brownian motion is actually like a pretty difficult problem, right? Like super research topic.
Yeah, it is a very emerging research topic. Yeah. So, don't you think that the partial differential course is not very like just for the exam, it is a research topic you are studying? Don't you feel like this?
Yeah, of course. Yes, yes.
Yeah, so every topic like whether it was Laplacian or whether it was the conservation law, I have tried to explain in a research way so that when you are going to start your research problem in applied mathematics, then it would be very easier for you. And this is the content of the course. It is not from my side, so don't worry. This is a master and graduate program, combined master and graduate program. So fundamental solution, I would explain the fundamental solution in two ways. One that is very easy and that is known to you, that is the variable of separation method, and another I will take a particular form and then we'll derive the fundamental solution and then we'll write the heat kernel. So I am going to proceed in a simpler manner like the variable separation method, but not the variable separation method which I have given. I will make an assumption here. So fundamental solution of the, this I haven't written in your notes. I have written the proper method which is given in Yvonne's book, but I think before going to that method, this explanation is how I can say, this explanation is the base of that method. So if u x comma t, suppose I'm just putting z because we are taking u in n dimensional, so each component is going to be solution of the heat equation. So if u say x comma t are solution to the one, just before writing this I would like to ask you one thing. The answer will be given by you, d2y over dx square plus y equals to 0. What is the general solution of this ordinary differential equation?
C1 sine of x plus C2 cos sine of x.
And if I say it y1 and I say it y2, so can I say that y1 also satisfy this equation?
Yeah.
So in the same fashion, since here it has n component because every nth order OD can be written as n cross n first order OD, so it has n component. Because of that, it will be the combination of the n solution. It will be the combination of the n solution, and each like u1 u2 un will go in each u1 u2 un are going to satisfy the heat equation u2 equals to uxx in the case when a equals to 1. So this is the criteria behind that. If you know this, then the statement is clear to you. So if you say x comma t are solution to the one dimensional heat equation, the equation ut is equals to uxx for x belongs to R and t is greater than 0, j is varying from 1 to n, then u x1 x2 comma dot xn comma t is equals to u1 x1 comma t comma dot un xn comma t is a solution of the n dimensional heat equation ut is equals to Laplacian of u for x is x1 dot xn belongs to Rn and t is greater than 0. You may do it as an exercise. That is basically coming from the variation of variable separation method. Next, again I am going to ask you a question and you are going to answer me. If u x comma t is a solution of ut is equals to uxx with x belongs to R, then so is w of lambda u lambda x. What will comes to this slot? It is x, it is t, and the equation is ut equals to uxx. So if lambda x is here, so what will come at this slot? If this is the heat equation, just try to understand. You know the answer, but I think you are confused. If I rescale x to lambda x, so we are going to see what will be the rescaling for t. So del u over del t is equals to del 2 u over del x square. Suppose we have rescaled to lambda x, then it will be del u and t is replaced with t tilde and x is replaced with lambda x tilde. So del u over del tilde del 2 u over, since I don't know the form of t, so I would derive del 2 u over del lambda x tilde square. So it will be del 2 u over del 1 over lambda square will be common. Del x tilde is square. So to cancel this lambda square, what kind of rescaling we need for t? To cancel this lambda square, what kind of rescaling we need for this t?
Lambda square by
Lambda square t tilde.
yeah.
So if we keep it here lambda square t tilde, so lambda square will be cancelled out and it can be written as this quantity. So what will be coming at this coordinate point? x is rescaled with lambda x, so t will be rescaled with, if x is rescaled with lambda x tilde, so t is rescaled with
lambda square t tilde.
yeah, lambda square t. I am not writing t tilde because we are suppressing the sign. So if u of x comma t is a solution of this heat equation, then this will also be the solution of this heat equation, and w lambda is appearing because of the lambda which will coming outside, it is going to cancel that thing for any real lambda. This is the very basic fundamental uh, dimensional analysis, but it is very easy, so that's why you are going to catch it very easily. Don't worry about that. And it is also known as dilation scaling. No, it is known as, yeah, dilation scaling. We are going to read this scaling in a detail in the next, but here I am trying to explain you the very basic of the heat equation, the very basic solution of the heat equation. So we can say that, especially we expect to have a solution of the form u of x comma t. Suppose I replace this lambda with um, I replace this lambda with 1 over t. No, so u lambda x comma lambda square t. If I replace this lambda with 1 over x, if I replace this lambda with 1 over x, so what will happen? Or you can say that if I replace lambda square lambda with 1 over square root of t, in any case what will happen? Suppose this is a dilation scaling, I replace lambda with 1 over x, so it will be x over x comma t over x square, isn't it? Or you can say t over x square. Or suppose if I replace lambda with 1 over square root t, if I replace lambda with 1 over square root t, then u x over square root t comma t over t, so this will cancel out and we are left with x over root t comma 1. In both the case, since this rescaling holds for the solution of the heat equation, so that the solution will be either of this form or this form. Since here u of 1 comma t over x square, so this one coordinate is 1, so that is constant, so it is varying with only one variable t over x square, or you can say that it is varying with only one variable x over root t, or simply you can say that it is varying with only one variable x square over t. Is it clear?
Yeah.
So in the scaling, when lambda is scaled with 1 over root t, what will be the w lambda? Isn't it? It will be function of t. Since we are rescaling, and in the rescaling I am taking the rescaling variable 1 over root t, so this was function of lambda, so it is going to be function of root t, or if I square, then isn't it w is going to be function of t?
Yeah.
Okay, this thing is a very basic thing, but it should be very clear to you. I haven't explained it in your notes because I don't think that you need. I need to write it in the notes. So, especially we expect to have a solution of the form u x comma t equals to w t v of x square t. In the bracket, let me write. I have taken the rescaling lambda to 1 over root t. This is a dilation rescaling. So if we implement this form of u in the equation ut is equals to uxx, so we need to know the derivative of this u with respect to t and the double derivative of u with respect to x. So can anyone tell me what will be the derivative of u with respect to t? Please do the calculation and let me know about that. Today is assume that it is your examination whether you are able to write the derivative or not. What will be the derivative of this u with respect to t? It was very easy thing. Why you are taking a lot of time? If you are unable to do, then please let me know. I will do that. But please say something.
It's the derivative of w
Hmm.
multiplied by v
Hmm.
multiplied by x. Yeah. Then it's minus
Hmm.
wt
Hmm.
v.
V dash t, na? V dash x
Oh
square.
yeah,
Yeah.
yeah, yeah.
And then
And then you have the 1 over t squared.
x square over t square because
Yeah.
yeah.
That's the argument.
Yeah, so this is a general function because we don't know the form of w, so this is the derivative with respect to t. In the same way, I am not going to do the whole calculation. I am simply writing. I just wanted to check you whether you are understanding the thing. So since you guys are understanding, so it is really easy. You can write here ux for your sake of convenience. So in the derivative with respect to x, w is going to treat as a constant because we are taking a partial derivative, and w is solely depending on t. W solely depending on t, so wt will be as it is, and v double dash x square over t 4x square over t square plus w of t v dash x square over t into 2 over t. Now, in order to satisfy the heat equation, this in order to have a solution of this heat equation which should satisfy the heat equation, so just substitute it in the heat equation. So in order to satisfy the heat equation, ut is equals to uxx. If you want to read these things in a detail, so everything is coming from the Evans book. Everything what I am writing here, I am just writing its easier version because the Evans has a very higher version, so don't worry about that. So w dash t v x square over t minus wt v dash x square over t multiplied with x square over t square and minus u of xxx. So minus wt v double dash, it is the augmented function of x square t multiplied with 4x square over t square minus w of t v dash augmented function of x square over t into. Please cross verify my calculation because I am very bad at calculation. Or you can write w dash of t v of x square over t. Just take wt outside of the, actually this is basically the variable separation form, so I will separate in one solely function of t and solely function of x square over t. So that is my aim to do here. V double dash x square over t multiplied by x square over t minus v. It was I think one derivative only, yeah. V dash, no, v double dash, it is one dash, v double dash x square over t into 2. I'm making a mistake, sorry. T into x square over t plus v double dash x square over t into 4x square over t plus v dash x square over t into 2. Now for the sake of convenience, assume that just wait, yeah, for the sake of convenience, assume that assume x square over t is equals to s is another variable, x square over t is another variable. Then substituting it in the above equation, it will give w dash t v of s minus wt over t, the double derivative of v into 4s because x square over t is s plus s v dash of s plus 2v dash of s. Can you guys see something beautiful here? What is clicking in your mind? Hmm?
Um, I don't know. The thing in brackets has some form.
You cannot see that. It can be written as t w dash t over wt minus, just send it this side. Oops, sorry. Let me write it like only yes. I am going to use two things, s plus 2 v dash s is equals to 0. Cannot you see that this is function of t and this is function of s? It is a very beautiful thing. Now you have separated it in the function of t and in the function of s. So then separation of variables is that it should be equals to some lambda, isn't it? So this thing is clear or not? You guys are not saying anything. Do you guys have doubt?
Yeah, it's clear.
Okay, then fine. Now take this with this. So you will be getting
Um,
the
I
yeah.
have a question, a big, big, big question that I have waited since we started this course to ask, and it's um, that is there a way to know what kind of constant, positive, negative, or zero
Mm-hmm.
would be like the separation variable, the separation constant? Is
Yeah,
there like
any, yeah.
any easy way to prove or to test that constant?
Mm, I would say that in the case of this, that was the issue. Let me ask you some question. The answer you already know, but let me ask you. In the case of the Laplacian equation, do you guys remember even this equation was going to involve the second derivative? And this equation was going to involve the second order derivative. So because of that, we have some restriction on lambda, isn't it? And the lambda was like the solution was going, we were using the Sturm-Liouville theorem. But here, this equation has first order derivative and this equation has the second order derivative. So somehow it we are able to write it in the form of the separation of variable, but it is little bit difficult than the Laplace case, isn't it?
Yeah.
Because here you won't be able to apply the Sturm-Liouville theorem like lambda. We were getting the solution lambda square. No, lambda is equals to say some beta square, and lambda is equals to say some minus beta square, and lambda is equals to say some equals to 0. So the I wanted to solve this question today, but now since Yvonne asked me a question, and I am going to ask you, this is your homework. You need to do a workout, because if I am going to tell you at the very first step, then you won't be working with your mind. So I would like to ask you, please discuss these three cases. Please discuss these three cases and let me know what is happening. Will you be able to do this or not?
Yeah, I think so.
So
Yeah.
please discuss these three cases, and the next in the next class I want to be hearing the excuse that you did not do this, because today my plan was to extend the class and to write the whole fundamental solution. But since you have your exam and this is the very basic things which we have done in the Laplacian equation, so I would like to ask you, please do this analysis, and in the next class I will only write the solution when you will be coming with the analysis of this. This will take only 15 minutes. So do this analysis, write the value of lambda like beta square minus beta square and lambda equals to 0, and see what is happening. See what is happening. So this is your homework. If you have any question, then you may ask. Do you guys have any question?
Now I feel guilty
Hmm?
for now I feel guilty for uh assigning this task to everyone.
Sorry?
I
Feel
feel
guilty.
guilty for
Uh-huh.
asking and
Mhm.
then transforming like the class to assignment.
Ah, no, no, it is not. Like, it is a good thing that you ask. In this way, you guys will be able to do the actually the exam is nearby, so that's why I am asking to solve this, because in this way you will be able to revise your Laplace cases. So that's why it is good. Like, I have cleared the most difficult part. It is not clear. Is it clear? Sorry, is it difficult? Is this part difficult? Which
No,
I So just I discussed the difficult part. The difficult part, how the rescaling is coming, and how you are applying the separation of variable. It was the difficult part of the heat equation, in my opinion, and I think it was the difficult part in your opinion as well, because proceeding with the solution of the heat equation is difficult than proceeding with the solution of the Laplacian equation, because it is involving the first order derivative with respect to time. So I have solved the difficult part, and you guys have pretty much idea how we are taking the solution in a variable x square over t. Actually, we are going to do the same thing for the wave equation as well. In the wave equation, if you will do the rescaling, then you will get to know that the solution will be coming like x over t, because uxx and utt, isn't it? Utt uxx, so it is coming to be solution of x over t. And this is a research problem. When we solve the
um, what's the purpose of the rescaling?
just go through the notes, just go through this derivation, and you will get another. If you want, then I can explain it again. You want explanation again?
No, no, no.
Let
It's
me
okay.
explain it again. It's fine. Another,
Yeah.
it is
Well,
my
well
duty. If you will ask me 10 times, then I will tell you, because
no,
it
no.
is the base. Yeah, it is the base. So the process of rescaling is that if you are changing the one coordinate variable with some like x with some lambda of x tilde, then you need to find what kind of rescaling will be applied on t. So that you just put and then see what is the form of t is coming. So that form of t over lambda, or lambda into t, that will be t tilde. So that is just a very simple way. I would like to say that I am just multiplying something and dividing something, isn't it?
Okay.
Yeah. I, like, you guys can discuss. I think Camilo is very clear with the rescaling. That's why he's
Camilo is great.
Camilo is great. Okay, so everyone make a call to Camilo.
Yes.
Okay, so have a nice weekend to all of you, and see you guys on Tuesday with your exams. And I want to be able to take a class on Monday, so I will postpone one class to next week. I was planning to take the class this Thursday, but I want to be able to take the class. I have a lot of work. So I will schedule, but you guys are pretty much on track. Don't worry about that. Your syllabus is going to finish on time, and you have studied all the topics in all the unit. Nothing is left.
What we should expect on Tuesday's exam? Like one problem for every subject or
Only unit 3. Only unit 3.
okay, only unit 3.
Only unit 3. That is just a
Okay.
practice of your, because unit 3 was really very heavy. It took me, I think, more than a month. Isn't it, Camilo? It took me more than a
Yes.
month to complete the unit 3, I think, because I wanted to explain the unit 3 in such a way that it should be very clear to you physically and as well as mathematically. So I try to put all my energy to explain it, because as soon as unit 3 is clear, unit 4 is going to be super easy to all of you. Unit 4 is nothing. In my opinion, I feel that unit 4 is the easiest. Okay, so have a nice weekend to all of you. Roberto, please join for the exam. Okay? Yeah. So
The questions will be like assignment level.
um, yeah, yeah, the
Okay.
question will be the same. In the previous exam, I gave the same type of question. So I always put the question like you have solved in your assignment and you have done in your class, because it is most important thing. If I am going to ask something very new or something very different from the topic, then you are not going to utilize your knowledge which you have grasped during the class. So that is my most uh, that is my aim, to make a question paper which is based on the assignment questions and the questions which I have discussed in the class. Because if I am asking something new, then that is going to waste my time and as well as your time. Okay. Yeah.
Okay.
So bye.
Bye.